This is my lab report for the Faraday's Law Lab. This lab will explore the forces created according to Faraday's Law. The purpose of this lab is to simulate and graph the forces created by Faraday's Law interactions, and the results will show in the form of a graph that the velocity stops changing inside the metal tube. The surroundings is my house and a smartphone. The system is the magnet and the aluminum foil tube. Initial conditions: the aluminum thickness was 1 inch, the tube length was 12 inches, the tube diameter was 3 inches, and the magnet weighed 68 grams. So in the code we use Biot-Savart law and Newton's third law to calculate forces. Faraday's law is used to calculate the current in the rings. Newton's second law is used to calculate position and velocity. And also, the tube is an array of ring objects that are stacked on top of each other. And so we have a loop in the code that will calculate the forces in the system for each ring as the magnet falls, and it will also update the magnet's position so we can move through all of the rings. So here's a screenshot of the simulation, and you see a red band and a blue band. Those are those different colors represent the field curling in opposite directions. And this is our graph. So I said earlier that the velocity stops changing, so the acceleration is balanced up and down, but since we had an initial downwards velocity due to gravity, the magnet still falls all the way through the tube and to the ground, but it does it pretty slowly compared to if it was just gravity. It would happen a lot faster. So the mu of the magnet was difficult to calculate and therefore is probably not correct. And the magnet was weighted on a metal scale which it was attracted to, so I may have not gotten the right weight measurement for the magnet. So interpreting the simulation, the magnet is dropped with its north pole facing up, so the induced current is clockwise. Red is on top, so red is clockwise, and then that clockwise current also creates another current under it, which is counterclockwise. When you flip the magnet around, red is on the bottom and blue is on the top, but the magnet follows with the same speed because it's the same pushing force. When you flip everything around, it sort of ends up with the same result. The time in the tube was greater than in the real world system. I think that if we added more rings, the system would be more accurate. And the force of gravity and force of the magnet became balanced while in the tube, but the velocity slipped downwards because the magnet gained some downward acceleration before inducing a current. However, if the resistivity of the conductor was reduced to almost 0, the magnet actually wouldn't fall down. The magnet would bounce up and down in the tube, but that's really not possible in the real world to have 0 resistivity. If holes or slots were cut into the tube, it would fall faster because while it's falling past that slot or hole, it would not be able to create the curly magnetic field to push it upwards against gravity. So conclusion, Faraday's law means when a magnet is dropped down a non-ferrous metal tube, it induces a curly magnetic field in whichever direction pushes the magnet in the opposite direction of gravity. The velocity does not change while in the tube, but the magnet still falls down because it has downward velocity when it induces the current.